in this example, we're going to look at titration of a weak acid with a strong base. So we have a volume and concentration of our weak acid, acetic acid, and our concentration of our strong base. We're going to calculate the pH at the following points. The first one being before the titration begins. So since we have two values, we have the volume and concentration of acetic acid, we know that we're going to be able to find the pH of the weak acid in equilibrium with water. So we're going to use an ice table, and we're going to find the concentration of hydronium based off of our ice table. So we have 0.300 moles per liter. We can use the approximation method. If we divide this by 1.8 times 10 to the negative 5, which is the Ka of acetic acid, it is greater than 500. So we know that we're going to have minus x, and this will be 0.3. We're going to be plus x here, and it will just be x. To solve for x, we would take 1.8 times 10 to the negative 5, which is the Ka of acetic acid, is equal to x squared over 0.300. This gives us an x value of 2.3 times 10 to the negative 3. To solve for the pH, we know that this has 2 sig digs here from our Ka value. Now our pH is going to be negative log 2.3 times 10 to the negative 3. Our 2 sig digs are going to turn into 2 decimal places. Because this is hydronium concentration, I know that this is pH and not POH. It's going to be 2.63. Now, after 10 milliliters of base has been added, we must do a stoichiometric calculation to figure out how much acetic acid is left. So we're going to be looking at a comparison to find the limiting reagent. So first we need to figure out the moles of our acid and the moles of our base. Our acid we know is 20 milliliters times 0.300 moles per liter. This gives us 6.00 times 10 to the negative 3 moles. Our moles of our base is equal to 0.010 liters, because we have 10 milliliters, times 0.300 moles per 1 liter. So we can see that we have more moles of our acid than of our base. And our acid will be remaining because we have more moles of it. So in this calculation, this is our limiting reagent. It will be completely consumed. This is our excess. And that's why we're going to continue with our moles of our acid remaining. So our moles of our acid is equal to our moles of our excess, which is 6.0 times 10 to the negative 3 moles of acid. We're going to subtract with the moles of our limiting, or how much we used of it. It's a 1-to-1 ratio. So we can do 1 mole base and multiply the acid, so it's in terms of what we want. And we're going to be left with this many moles of our acid. Now we've joined two volumes, so we need to find the new concentration of our acid. So we know that we have this many moles of our acid, and the total volume will be 0.030. That's 0.20 plus 0.10 liters. This gives us a value of 0.100 moles per liter. Now, we also have to look at what's happening here. So we have our acid reacting with water to make this and hydronium, as we saw in our previous example. So we have a concentration of this, which is our new amount of 0.1, but since we added base, we also contributed to a new concentration of our conjugate base. So the moles of our base is used to find the moles of our conjugate base, because the moles of our base is equal to how much of our conjugate base was formed. This is a rule, okay? So now we know that our moles of our base was 3. So here's our conjugate base. The moles of our base is equal to 3.00 times 10 to the negative 3. Now the moles of our conjugate base is going to be 3.00 times 10 to the negative 3 moles of base. And it's a 1-to-1 ratio, so every 1 mole of base is equal to 1 mole of our conjugate base. Our new concentration of our conjugate base is equal to 3.0 times 10 to the negative 3 divided by our total volume, the same total volume as for our acid, and this gives us 0.100 as well. Now we have 2 things to put in our ice table. First, we'll start with the reaction. We have 0.100 moles per liter of acetic acid. We also have that for our base, conjugate base, based on what we had from our base. We can check the approximation for both of them. Just so happens that they're the same number. It's greater than 500. So at the end, we're going to have minus x, 0.10, plus x, 0.100, plus x, and x. Now we can solve for x. 1.8 times 10 to the negative 5 is equal to 0.100 x over 0.100. I can see that these cancel out. And I have 1.8 times 10 to the negative 5 is equal to x. Again, we have 2 sig digs. We're going to put that into our pH because it is our hydronium. pH is equal to negative log 1.8 times 10 to the negative 5 is equal to 4.74, 2 decimal places here. Okay, so that again is for after 10 milliliters of base has been added, and we also did before the titration begins. We're going to do a new video for add equivalents and beyond equivalents.